Scribble it out. For those of you following at home, we did least common multiple of 5 and 7 is 35, of 10, 15, and 20 is 60, and of 15, 40, and 100 is 600. This took us some guessing. So here's a method that can get us there, and you want to leave stuff in exponential form. And here's what you want to do. Look at the 2's. What's the biggest power of 2 in any one list? 2 to the third? So let's write that down. What's the biggest power of 3 in any one list? Let's write that down. I'll put a little 1 there so that we actually said that. What's the biggest power of 5 in any one list? Try multiplying that together. Do we get 600? Yeah. We do? Yes? Yep. Did you have your calculator? I won't even ask. So scribble this out, because that's not the correct explanation. I think what happened is I accidentally cut and pasted my GCF explanation to here. Silly of me. It is 600, yes? So if you're given something really big, now Garrett, I still think the best way is to guess and check and just try and get there quickly for small numbers. But if you give me huge numbers, did we learn how to do the prime factorization last day? Yes. Can I do that? Yep. List all my prime factorizations, and then it is the biggest exponent on each prime factor. Yep. Let's try another one, see if I can recover. Use the prime factorization method to determine the least common multiple. Example 9. 15 and 35. All right. 15 equals what? Yeah, turn the page. I'm going to go smallest to biggest, 3 times 5. 35 is what? 5 times 7. So the least common multiple is going to be, I need how many 3's? There's 2 3's somewhere? Need 1 3. What's the smallest exponent of 5 that appears in everything? 1. There's 2 5, 1 5 in each, but what's the smallest exponent that appears on any of those 5's? A 1. What's the smallest exponent that appears on any of the 7's? That's your least common multiple. What is 3 times 5 times 7? 105? Nice. Let's try B, 126 and 441. Okay. Get your calculators out. We'll see if we can do this. Or you can do this without a calculator, factor tree, but what's a prime number that goes into 126? 2 times what? I'm going to go with 63. Yeah, 63 is what times what? I know it's 7 times 9. Yes? Yeah? What's 9? 3. I think it's this. In my mind, I'm seeing this. 3 squared and 7. Yes? Yes? No? Did I lose somebody there? Was that what? Lost or what? Something else? Okay. 441. What goes into 441? Certainly not 2. 7 goes into 441? How many times? 63. So in my mind, or off in the margin here, I'm going to see 7 times 63. I'm really going to see 7 times 9 times 7. I'm really going to see 7 times 3 squared times 7. You see what I'm really doing, Ben? I'm doing a divisibility table, but I'm doing it on the fly off in the margin somewhere. How many 3's and how many 7's are there really in the prime factorization of 441? L, C, M. How many 2s do I need? How many 3s do I need? How many 7s do I need? I need 2, right? That's going to be the least common multiple. 3 squared is 9, 7 squared is 49, 9 times 2 is 18 times 49. Well, 18 times 50 would be 360. I'm going to go with 334. Am I off? No, I'm wrong. What is it? 800. Wow, I'm way off. 882. Wow, I was way off. But I am going to suggest, Alex, that method, even though it was a lot of writing, for that big numbers is probably faster than guessing and checking. Because most of you would have done this. You would have said, well, I know this trick works. 126 times 441. And then you would have tried to whittle that down. Yeah.
Or you could double 441 and then times 126 by the number of 2 together.
Like that?
No, like...
That's what you're saying. You're saying, take one of your numbers, start multiplying it, and then see if the other one goes into it, because if it does, it's an LCM. Sure. Only risk is that works great if 441 times 2 works, but what if it had been 441 times 19? And you would have had to do all those first, and then work your way backwards. So, or what if there's 3 numbers, like C? Like C. So now it says, find the GCF of those. Okay, let's list the prime factorization. 22, I think I can do in my head. 22 is what times what? 2 times 11. 154. What's 154 divided by, I know 2 goes into it, divided by 2? 77 and 2? I heard Kira say it, 2, 7, and 11. Because 77 is, right, or 11 times table. 198. Try 2. 2 times 99. And what would 99 be? 3, 3, and 11. 2 3s and an 11. Like 9 times 11, 3 squared. Okay, so a 2, a 3 squared, 9, and an 11. Okay, here we go. So what is the least common multiple? How many 2s do I need? At least 1. Let's go in order. I see 3s. How many 3s do I need? 2. How many 7s do I need? How many 11s do I need? 1. What is the least common multiple? And I dare say that would take you a while to find otherwise. Okay. Prime factorization of perfect squares. What are perfect squares? Well, 1. What's the next perfect square after 1? 2 times 2 is? 4. Then what's next? 9. Or is that a German saying no? I'll never get tired of that joke. Next.
15,
Keep going.
25,
Keep going. Oh, heck, keep going. 49. Then? 64. 9 times 9, 81. 10 times 10, 11 times 11, 121. 12 times 12. Those it's worth having. 13 times 13, 169. 14 times 14, 196, I believe. Double check me. Yes? 186. I always get that. 196? I did say that. Okay. 15 times 15 is 225. 16 times 16 is 256. 17 times 17 is, ends in a 9. 389? 289. That's what I said. Listen closely. 18 times 18 is 364. No, 324.
yeah.
19 times 19. All I know is 9 times 9 is 81, so 19 times 19 ends in a 1. What is it? 361. I know 20 times 20 is 400. It's worth having the first 12 definitely. Every perfect square has 2 square roots. One positive and one negative. And at the beginning, we're going to be dealing with the positive square root. The positive square root is called the principal root. What's the square root symbol? Does anybody remember? Yeah. It's like a check mark with do you know where it came from? Don't write this down. This is just Mr. Duke's nerdy trivia. For years, for a couple of centuries, they would write. And then a mathematician came along and said, instead of writing the word root, what would be a good letter to use as an abbreviation for the word root? What does that look an awful lot like? See it? It came from the letter R. Yeah. Square root of 9. 3. Or were you just saying no? It says, write each of the following as prime factors. How can I write 9? And the fact that 9 is 3 times 3, what that means is the square root of 9 is what? 3. Not 3 squared. The square root of 9 is 3. 3 squared is 9. That means that going backwards, Jordan, the square root of 9 is 3. 36. Well, if I write the prime factorization of 36, it's actually 4 times 9. It's 2 times 2 times 3 times 3. And you'll notice that there are pairs of numbers. Every number has a pair. That's another way to tell that a number is a perfect square. If, when you do its prime factorization, you notice every single number comes in 2s. There's 2 2s, there's 2 3s. What's the square root of 36? Can you see it hidden in there? There's 1 2 and 1 3. If I write the prime factorization of 49, it's 7 squared. It's 7 times 7. The square root of 49 is 7. What about, you're right, but you're saying it wrong. What about 6? For like 64? Or what are you asking? No, you're actually righter than you realize. If I write the prime factorization of 64, you know what it's going to be? 2 times 2 times 2, 4, 8, 16, 32, 6, not 64, Mr. Duke, another 2. 64 is actually how many 2s? Amy? 6 is correct. It's actually 2 times 2 times 2 times 2 times 2 times 2. Or if I pair them up, it's actually 3 sets of 2. But we don't write 2 cubed as its square root. What do we write? What is 2 cubed? 2 to the 3rd power? 8. Square root of 64 is 8. But I am showing you a different way to find square roots on the fly. The prime factorization of perfect squares will involve factors which occur in pairs. Should be an S right there. If the prime factorization of a number does not result in pairs of factors, then we can say that the number is not a perfect square. So if I go back, you'll notice the prime factorization of 198, we didn't end up with a pair of 3s, but did we end up with a pair of 2s or a pair of 11s? Then it's not a perfect square. It's another way that you can tell without your calculator, Alex, if you don't have your calculator handy. If you get a really big number and you're asked, is it a perfect square? Write its prime factorization. And if every number doesn't come in groups of 2s, or groups of 4s, or groups of 6s, or groups of 8s, if there's not an even number of each factor, it's not a perfect square. Is that okay? So, what about the prime factorization of a perfect cube? When I say cubed, what exponent am I talking about? To the 3rd. Perfect cubes include 1 to the third, which is 1. 2 to the third. What's 2 to the third? 8. What's 3 to the third? What's 3 times 3 times 3? 27. What's 4 to the third? What's 4 times 4 times 4? 64. What's 5 to the third? What's 5 times 5 times 5? 125. What's 6 to the third? It's 216. Those are the ones that I have memorized. Oh, well, I know 10 to the third. 10 times 10 times 10 is 1,000. I got that one up here, too. But if you ask me what 7 to the third is, I know I'm going to guess 343, but it would have been a reasonable guess. But those first 5 or 6, I got those ones. It says, find the prime factorization of the following perfect cubes. 27, the prime factorization is Yeah. 216, the prime factorization, as it turns out, is 2 times 2 times 2 times 3 times 3 times 3. Can you see how there is 3 of each number for a perfect cube? How do we write cube root? Well, how do we write square root? What was the symbol for square root? Alex, you pointed it out. You said it looked like what letter? Okay. You can all write this down here. That's not the cube root. That's the square root of 216. Does anybody know how I turn that into a cube root? It's actually a nice little system. Right here, I put a 3. Now it's cube root. Why did I put a 3? It's because it comes from cubed to the third power. In fact, we would say this. The cube root of 27 is 3. The cube root of 216 is 6. What's the cube root of 3,375? Hey, let's write the prime factorization. What's 3,375 divided by 3? Does 3 go into that? What'd you get? Does 3 go into that? Does 3 go into that? You don't need to try. Add them up. It doesn't. What goes into 125? 5? Does 5 go into your new answer? And does 5 go into the final answer? Anybody tell me what the cube root of 3,375 is? 15. See it? 3 3s, take one of them. 3 5s, take one of them. So the prime factorization of a perfect cube will involve sets of factors where each factor occurs 3 times. Hey, let's extend this. What if I asked you for the 4th root? How many of each prime factor would appear? 4. What about for the 5th root? 5. Oh, let's generalize it. What about for the nth root? N of them, whatever root. What about for the 17th root? We never really use that, but what about for the 17th root? You'd be looking for 17 of them. Hey, Mr. Duick, is this somewhere on my calculator? Have I got a cube root button? Yeah. Now, where it is varies. On my graphing calculator, it's right there. That 3 is supposed to actually be inside the little V check mark, but the graphics can't quite do that. That's saying cube root of, and I know that the cube root of 1,000 is 10. So what you want to do right now, assuming you have a good scientific calculator here, is to see if you can find where your cube root button is right now. I'll come around and help.